an NMR sample. And because we are not people here, it's hard to really do something, but I will take you and explain you some basic stuff for the equipment and the chromatography, and you get a taste of what we do here. Okay? So I guess if you followed Dr. Kelly's lectures, he explained to you that here we are a protein NMR lab. So what we do is we produce proteins, and the goal is to study them using NMR. And what we want to study is to get the structure of the protein, to study the interaction of the protein with another protein, with a ligand, and so on. So it's protein-protein interaction and structures. Do you have your own chemistry majors? So have you been to an NMR? Do you know how is an NMR? You've been to an NMR, so you know more or less what we are talking about. So the NMR, unfortunately today I cannot take you to the actual place where we have the NMR instrument. Here is what we call the wet lab. Here we prepare the sample. The NMR sample, I will go to the end and then we go backwards to tell you how we end up here. Usually our sample will end up in a tube like that. So we are working to get a 300 microliter sample of the protein. As I said, it will go to NMR. So NMR is for those who have seen NMR, it's a huge instrument, and you have this guy going inside. Okay, so the first step is to express the protein. But in fact, the first step is to clone the protein that you want to study. Okay. So to do cloning, you need to do a careful design at the beginning, because you need to include in the cloning strategy different features that you need for the protein in order to facilitate the purification of the protein. Alright? So at the very beginning, you need to check what tag are you going to use to isolate this protein. Meaning, am I going to use his tag? Am I going to use a GST column to isolate the protein, and so on. So after you do a careful design of your construct, what then you do is you need to find your DNA, which we either order synthetically, we just order the DNA of interest, or like sometimes there are some gene banks that you can again order, and they send you a plasmid from where you can copy what is interesting for you in any particular case. Okay. So after you have that, you have decided which piece of DNA are you gonna amplify. Then first, the very first thing you do is to do PCR. Our PCR is here, so maybe you have seen that before. This is called, it's a thermocycler. So what we are doing here is you assemble a reaction that has all the necessary components to give you at the end a good amount of DNA, which you're going to use later to do your cloning, and later to use the plasmid that you generate to do protein expression. Okay? So in fact, this is the very first step. So for PCR reaction, just to give you an idea of quantities or how big the volume of a reaction is, like 50 microliter. So you assemble a reaction on these tubes, and here we play with very small volumes in the order of 1 or 2 microliters. We use micropipettes. One thing is that here everything should be sterile and clean, because you want to avoid any contamination of any other DNA, because let's say even my hands, they can bring contamination to my reaction. So you try to be clean as possible. So we use filter tips and all this kind of stuff. And then after you assemble the reaction, just to say here, as I said, you need, for a PCR reaction, you need the template DNA, the DNA from where you are going to copy what you want. Then you need what we call primers. The primers are the two small pieces of the DNA complementary to the end and the beginning of your DNA piece. It's like the flags that they say, start to copy from here, stop copy here. And then you need the NTPs, the nucleotides, and of course the polymerase. Okay? And after you assemble in the appropriate quantities, everything here, and you come here and we have a program that we just run. So in a PCR, what you're doing is that you play with the temperature here. In order to copy the DNA that you want, you need, first of all, the very first step of a PCR reaction is to denature the DNA. So we go to a temperature of 9800 degrees, and that, you have a double helix, which of course at that temperature will open. That's the very first step, which we call initial denaturation. Then we have, for those you are close, you can see that, and then we can kind of move a little bit. There is a program that you have these steps going here. You have the very first initial denaturation, then the steps 2, 3, and 4, they will repeat it in order at the end to get a good amount of DNA. And the step number 2, the first step is called, as we said, denaturation, which is followed by what we call annealing. Annealing is the point that the primers will stick, find the complementary ends of the DNA, will stick there, and then you have the extension. After this, the polymerase will jump into and start adding nucleotides, and then you end up with a piece of DNA, all right? Then you repeat this process 30 times. This is an exponential process, so it means that every cycle after every cycle you're gonna get more and more and more. And after that, at the end, you always, if you have a successful reaction, you have a good amount that you can go and follow the next steps. So here what I want to say is that you work with an enzyme, a polymerase, and you work at temperatures close to 100 degrees. In theory, can somebody explain why an enzyme can live at 100 degrees Celsius? So let's say if we isolate a polymerase from human cells and you use it in this reaction will not work, because at this temperature the polymerase will be dead. So we are using here polymerases that are resistant to high temperature. These polymerases, they have been isolated from bacteria that survive at temperatures, at hot springs and all this stuff. So it's something good to know. So after you get your DNA here, you need to analyze it. So I'm gonna look at this part. So on that side, here we have the banks. In this food, we work mainly with the DNA. The DNA, you can run it in an agarose gel. Have you seen agarose gels? Yeah. So you know DNA electrophoresis. So you run it on a horizontal, like here, if you can come afterwards. You can see the devices, and then you can visualize the DNA in the UV lamp. And what we have here is we stain our gel, or when we prepare our gel, we add some ethidium bromide, and ethidium bromide specifically can bind to the DNA, and that gives us the ability to observe it immediately. So we put it on the lamp, we have the UV lamp here, we switch it off, and then immediately you can see your DNA. Because in the PCR you set up everything, but you need to see that at the end your reaction worked, because it's not always successful. So a way to immediately see, which is the best, is to run an agarose check. And after you confirm that you have the correct DNA, what you do is you introduce it into a vector. A vector is like another DNA, a standard DNA piece that has many features that will facilitate the protein expression. Because as it is a piece of DNA, you cannot put it inside the cells and start producing protein. This DNA, if you try to do that, it will immediately get degraded and get lost. It will never give you a protein. That's why what we do is that we use a plasmid that has a promoter for the polymerases to start producing the protein. It has also antibiotic resistance and everything. So after the cloning, what you do is you have a vector of your choice, and then you have the piece of DNA that you want to introduce. It's like you leave these two things, and the enzyme is doing that, is a ligase. So you have a circular plasmid at the end, and this is what we introduce to bacteria in order to give us next step protein. So I have here so after having confirmed by sequencing our plasmid, what we do is what we call transformation. We transform this plasmid into bacteria. There are many different strains of bacteria, so again, according to your research, to the protein properties and everything, you pick the one you need, suitable for your needs, and you transform. When we say transformation, we mean that it's the process of introducing the plasmid into a bacteria cells. So, and to do the transformation, we have special cells that we call competent cells. The competent cells, the characteristic is that they have like opened the membrane, because the plasmid, what we call plasmid, is not a small piece of DNA. Usually it's like around 7,000 base pairs, so it's a big piece of DNA. And of course, the cells, they have pores on the membrane that they can communicate with the outer space, but they don't allow such big pieces to come inside. That's why we take special cells, the competent cells, and we mix with our plasmid. We follow like a heat shock processing. Excuse me guys, I'm a little bit sick. Not much, don't worry, it's just congestion here. Nothing to get you sick. So our plasmid, as I said, we designed it like to have antibiotic resistance. And this is a thing that gives us security that what we grow, what we observe every time, it's our own plasmid and not contamination from something else. Okay, so this bacteria here, after transformation, they acquire resistance to kanamycin. Kanamycin is an antibiotic, and this is because my plasmid has a specific feature that gives an antibiotic resistance to kanamycin. So if I put on this plate bacteria that they have ampicillin resistance, you will take nothing will survive. If while here you see all these white spots, it's what we call colonies, and these are bacteria, E. coli, that they intake the plasmid. And this is the starting point. From that white spot, we can pick this colony and propagate it in larger cultures and finally extract our protein from here. So the next step, we go on the other side. So in this part of the lab, we are doing more our what we call cultures, bacteria cultures. The starting point is this one colony, and then from here we are going to liquid cultures. Depending on what kind of isotopic labeling we want to do, we are using a different media for our expression. In the NMR, probably you know that not all the isotopes are active. So for a protein, in order to analyze, to observe, to record data in the NMR, you need to have either N15, while the natural evidence is the N14, C13, or the proton, which is NMR active nuclei. Okay? If we just want to grow a protein, what we call unlabeled, and we study just the proton NMR spectrum, we use media that we call LB or Luria broth media. These are usually like this. They are yellowish, and we make them. Everything should be sterile here again. We're still working under sterile condition and under antibiotic. All our cultures, they contain antibiotics inside. So what we do is we pick a colony, but we don't transfer it, let's say, to a 1 liter media. Okay, this is another type of media which we call M9 or minimal media, and we use this media when we want to introduce labeling. These media, they contain all the essential salts and minerals and everything, the absolutely necessary stuff. And then what we do is we can supplement this media with ammonium chloride N15 label, if we want to produce an N15 label protein, or carbon C13. We give glucose, that is C13, so they eat that glucose and they produce protein with C13 labeling. And the first step is so this, in order to go from this step, from the colony to the liquid cultures, we use the incubator here because we need to have it kind of isolated, so again, to keep it clean and avoid any contamination. And then you need also to regulate the temperature, because bacteria, they like and they grow very nice at 37 degrees Celsius. And also you need the shaking, because if you take a flask with media and you inoculate it with bacteria and you leave it steady, the bacteria will die because you don't have air getting inside the flask. So you need a combination of temperature and shaking at the same time in order to propagate the growth. And what is happening now? This is not so visible already. Let's see if we have a better example. Yeah. I'll show you this. So if you see this here, you almost see nothing. It's just starting to see like a cloud, but it's almost nothing, because imagine you take one of these colonies and you transfer it here. Of course, at the first time you're not going to see anything, but as the time goes, you get again exponential growth of bacteria, so you can see here almost very slightly cloudy, while here you can see all of you that we have growth. Okay. And then this is what we call is our starting liquid culture, and from this we again slowly transfer, and we go, after this we go usually to 15 milliliters overnight, and then next day we do what we call large scale, which can be 1 liter, 2 liters, depending on what you want to do, how much protein, how well a protein expresses, because unfortunately not all the proteins express very well, so some proteins are more difficult to get, so you may need to purify or to express 4 liters in order to get a good amount to make a sample. After we do our large scale, what we're gonna have in the flask that I just showed you in the 1 liter, this will get cloudy as the same with the small culture. So the next step is to take the protein out of this suspension, and we do that by first separating the bacteria from the liquid. So we are doing a first centrifugation, it's just a spin. Bacteria are pretty heavy in a way, so they will settle even with a low speed centrifugation. So you can very easily separate the pellet from the supernatant. The supernatant is not of interest anymore, so we disinfect it, we dump it, and we are done with that. All the material that we need is in the pellet, so but still this pellet needs some processing in order to extract the protein, because imagine you have an E. coli bacterium, the protein is like swimming in the cytosol of this. So you need to break the cells, to open the membranes in order to extract, to fish out your protein from there. To do that, we are using to break the membranes, and in general to break the cells. You can come from this side if you want, guys, half and half.
Trying to get the protein out of our bacteria.
Alright, so after you do your centrifugation, what you do is you have this pellet. But to process this pellet, you need to resuspend it in a buffer. From now on, we are going to have our protein, or the suspension that contains our protein, in a buffer. The choice of the buffer depends on the protein. So you need to check the physical properties of your protein. Means, first of all, the pI, the isoelectric point of the protein. That will tell you the pH which you allow to work, because if you go very close to the pI, the protein is going to precipitate, right? So You check the charges also, so you decide the salt that you're going to use. If you need some other additives, some proteins, you need also to add protease inhibitors because they are very sensitive to degradation. So to protect the protein, you just add some protease inhibitors. Okay? So this is like what we call here a resuspended cell pellet, and that we usually, if we are not ready to process it immediately after centrifugation, we can store that at minus 80 degrees, and that can survive. You can come closer if you want, guys. That can survive at minus 80 about 1 year, though we prefer to process our samples much faster, but it can be safe there. Can you put that back, Andrea, please? Put it somewhere and then put it in the proper place. So you fold the cells, and then, as I said, you need to break the membranes to open and get the protein out. So what we use is a sonicator that creates sound waves that will break the membrane. So what it is, the water you see here now usually is our bacteria, is the lysate. You have to be careful here, it's noisy, it's not gonna make a big damage to yourself if you have the door open, it's not so strong, but it's good to protect yourself and have everything closed here. And what we do is that we create pulses for a short time interval for 5 seconds, and then we give a break for 30 seconds because these pulses, they create heat. And the only thing that you don't want to introduce to your protein is heat. I forgot to mention that after the centrifuge, we don't work anymore to sterile condition, but we try to do everything at 4 degrees. Proteins, we want to keep them alive as long as possible, and one way is to keep them at everything at 4 degrees, so everything should be on ice. Even this sonication process, we have an ice bath and we keep it all the time cold. So as I said, we do 5 seconds on, 30 off to give it time to cool down, and then we go through this cycle for about half an hour. That is sufficient to break the cells. So that's what is happening. We have this wave and they break cells. So the next step is to do another round of centrifugation, because after the sonication you have a part of the bacteria which is insoluble. Is the bacteria, the membrane debris and all the stuff that is in a way also for us garbage. There is nothing useful for us there. Our protein hopefully should be in the solution. So we take the supernatant and then we go and to apply it to chromatography, depend again on what kind of design we did before. So we go again on the other side. So as I said, we do everything. So this is not
like
the system here. This is one type that maybe you have seen in other labs. This is again chromatography, but it's not on right now. But it's the same principle. What we are just, it's another type, more advanced instrument. It's nothing different. The principles are all the same. So, as I said, right now we have our lysate, the solution that finally has our protein inside. There are many different tags that when we design the cloning we introduce to proteins. The most common and the easiest because it's cheaper, it's easier to make, and everything is the histag. Histag is 6 to 9 histidines fused at the end of the protein, and histidine, if you have the structure in your mind, has affinity for metals. And that's why in order to capture this tag, we are using a resin that is charged with nickel. And this group of histidines at the end of the protein will make it stick on the column. So what we do first thing is to pass our lysate through this column. On the column will only stick the protein, only, I did close to only, usually sometimes you have some non-specific binding, what we call, but you can find, if you wash extensively with your buffer, you can get rid of these impurities and go to the next step with no other proteins. So the principle of nickel is that nickel it's an affinity chromatography, nickel, histidine, it binds. So the question here is how you elute, how you take your protein out of the column. Any answer? It's a general thing. Think about affinity. So you need to wash it out with something. So first of all, that always you want to find something that will not interfere with your protein, but you need to find something that will have higher affinity for the nickel compared to your protein. And this is a chemical, is imidazole. So to get your protein out of the column, because you cannot take the whole column and go to the NMR, you need the protein. You wash the column with high imidazole, which is 400 millimolar, and that will release the protein because imidazole higher affinity for nickel, it displaces the protein and stick on the column. Okay. This is the first step of purification. That can be a nickel purification. Sometimes we have other type of columns. This is a GST column. GST is a glutathione transferase, is an enzyme that if you engineer it again to the end of your protein, you can use it to isolate it. This is another type of column that it's specific for only GST fused proteins. To release a protein from a GST column, we use glutathione, same principle here, again affinity chromatography. You have something that has higher affinity for here, so it's gonna displace the protein, so you take it out. This is the two types of first step purification that at least we do in this lab. There are many other types of purification. So then you need to see the purity of your protein and to see if you need to further purify it with more columns. If you run a gel and if you see that you have impurities, which is most of the times the case, you can you can do ion exchange chromatography, which you separate according to the charge here, cation or anion. And then what we always do, no matter what, because it's like what we call it like polishing, it's clean the protein even if it's quite pure. We do size exclusion chromatography. So size exclusion, do you see these long columns? So if you inject your protein solution into these columns, the protein will travel through the column and it will spend time in the column according to its size. So the larger the protein, and depending on the material that you have, but in general, the larger the protein, it will come faster out of the column because it cannot go through the pores and travel and spend more time inside the column. So it's very quickly getting out the large protein, and next you expect the smaller, and so on. Okay? So that's the principle of size exclusion, and you can have different types of size exclusion chromatography depending on the bead's size. So you can have a column specific only for large proteins, a column only for small. You can have preparative. You can see we have a column but it's wider than the other. So many different combination of bead size and diameter can facilitate your purification. I can show you here some examples. If you want to come, guys, if you want